Okay, now let's change gears a little bit. Another way of thinking about optimization is using reservoir simulation. And there was a very nice paper published in 2018 by Vic Sen and others at Anadarko. And in talking to Vic and Richard Sullivan at Anadarko at the time, we seemed to have very different perspectives of what was happening during the stimulation process. It turns out we had very similar ideas. We were just using different words to describe what was going on. Now, what they were doing is using reservoir simulation to match fracture treatment pressure. Okay, so they were simulating the hydraulic fracturing to match flow back and early production immediately after hydraulic fracturing, and then the initial decline curves. And then when they shut in a well and measure the pressure buildup, they're also going to try to match that as well. So the thing I really liked about this paper is that they were considering, they're using their simulator to match multiple data sets because it gives them just a much more robust idea of what's happening in the formation. Now, I kind of look at this process as a process in which we have a propped hydraulic fracture and then this shear fracture network surrounding the hydraulic fracture. And that's kind of what they're modeling too. They have a hydraulic fracture, which is propped, and then they call this, what they're calling the SRV, is the matrix of enhanced permeability. And so they're simulating what I refer to as slip-on pre-existing faults in this, what's seen in the microseismic cloud, as simply a zone of altered matrix and enhanced matrix permeability, and that's ultimately surrounded by unaltered matrix. Okay, and so really their view and my view is really quite similar. Okay, there's the hydraulic fracture and then this zone surrounding the hydraulic fracture of enhanced permeability. Now, the reason they were doing these simulations is they were trying, and these are 4 different unconventional plays, and in their paper they not only are illustrating what they decided on, but they're looking at different combinations of models that were tried and sometimes abandoned. So what you're looking at is a hydraulic fracture propagating from a perforation cluster in each way, and you're looking at the zone of enhanced permeability and how enhanced was that permeability that modeled the data. But what you can see is very different examples of how optimal a particular case is. So if you look at this upper left, what you can see is this zone of stimulated permeability is very narrow around the hydraulic fractures, and you're getting these big gaps between the hydraulic fractures in which, nothing is being produced. So these wells are clearly too far apart for the stimulation method that was being used, and they were leaving lots of hydrocarbons behind. The same thing, is true in this case here. In the case in the upper right, it looks like maybe the wells are closer than they need to be because everything is really well stimulated adjacent to the wells, and then of course becomes less well stimulated as you get further from the well. But nonetheless, if you're looking at the spacing between stages, they may be too close, whereas in these other cases they're too far. In this example in the lower left, we're approaching a happy medium. Most of the stimulation is close to the hydraulic fracture. There's less stimulation between, but it's much better than this case and this case, and perhaps somewhere between these two cases is what one might consider to be the ideal circumstance, where at least the spacing between the hydraulic fractures is appropriate to get as much of the hydrocarbon as possible. The other issue, of course, is where do you put the next well? And we're getting some idea here about the distance over which the fracture half length is being viewed not in terms of the fracture itself, but really in terms of how far away from the well are you really enhancing the permeability and increasing production. And so we're getting a more robust idea about fracture half lengths and well spacing, as well as stage perforation spacing within stages in this case as well. And they go through multiple examples of different cluster spacings and how much they're pumping per perforation cluster through this paper. It's really quite a comprehensive treatment. And I would argue that when we actually look at published data, and we in Table 11.1 we sort of published we summarized what we knew had been published. And frankly, these numbers are all over the map. I actually don't think these published values are of very much use. But I would argue that insight from simulation can be very important. In particular case for well spacing, but also for perforation, the separation between perforation clusters and so on. But one of the interesting aspects of this Sen et al. Paper is they also pointed out not only what do you know, but the question of when do you know it, okay? So this is all kind of normalized in terms of variations of well spacing, variations of completion size, variations of cluster spacing, production controls, which basically means choking the rate of gas production. And they are showing what the modeling reveals over different epochs of 3 months, 6 months, 1 year, 2 years, 5 years, 20 years, and so on. So let's start with production controls. What they're really showing here is that if you're choking back the well, it makes a big difference, in the first 1 to 2 years of production on, production rate. But after that, it doesn't really matter very much. And, whether you control production or not from this nominal value, whether you use less or more of a choke matters a lot early on and matters not at all over longer time periods. Perhaps a more sobering result comes from the well spacing. One of the huge questions, of course, facing every operator is what's an optimal well spacing? But basically what they argue is for the first 6 months and almost for the first year, there's not a whole lot of difference between very markedly different well spacings, but over 2 to 5 years, suddenly that the correct well spacing becomes obvious. And that's a really, I think, an interesting observation, and it tells us not to judge results, what we think is the wells are too close or too far based on, say, the first year of production may be premature, and the right well spacing may not be evident for until longer periods have elapsed. Completion size, it's kind of similar. It's kind of hard to tell what's going on. There's a little bit of a signal in the first few months, but it becomes more evident with longer time. With respect to cluster spacing, in the models they did, it doesn't seem to matter very much over different time periods. But of course, they're varying lots of things at various times. But I did want to show this to enter a note of humility and the ability to make inferences based on well performance data over short periods of time. And, with wells costing, something between $5 and $10 million a well, if you're drilling too many wells or you're not drilling enough wells, it's a absolutely critically important question. But you really don't want to be answering that question based on data that's available over time periods of less than a year, because the right answer may not reveal itself for much longer, and so on.